In this video, we're going to review some concepts about dot product and also extend our dot product work to some new things. So first of all, just a quick review of the calculation of dot product. Remember, it is the x coordinates multiplied together. So in our first case, we've got 2 multiplied by 6. I'm going to fix my 2 here. Okay. 2 multiplied by 6 plus 3 multiplied by negative 3. So 12 plus negative 9 is 3. All right. Next, we've got 6 multiplied by 3 plus negative 2 multiplied by negative 1 plus 1 multiplied by 5. So we've got 18 plus 2 plus 5 for a dot of 25. Recall that the dot product represents a kind of a scalar or a multiplier that says how is the initial vector being affected by this new vector. So you see that, I mean, this one, you're being pushed in the same direction, to the right, but in opposite directions in terms of y. One's going up 3, the other's down 3, and that's why it's a very small value. Okay, it's not a very large scalar. It's not a lot of quote-unquote power that's being added. Whereas here, you're being pushed in the same direction for every variable, and that's why it's a much larger dot product. Okay, finding the angle between two vectors. So if you recall, I'm gonna put this one down here. We dot the 2, so 6 multiplied by 5 plus 2 multiplied by negative 2 over, and then we do the magnitude. So 6 squared plus 2 squared, so this will be the square root of 40, and this one will be 5 squared plus negative 2 squared, so that will be 29. We're going to have 40, we're going to have 29. And this is equal to the cosine of theta, so we will take the inverse cosine of this whole thing, and that will give us theta. Okay. Now the beauty of dot product is that finding the angle between lines or vectors is not something that's that difficult to do in 2 dimensions. We got a lot of things at our disposal. We've got the trigonometric functions, we've got law of sines, we've got law of cosines, we've got a lot of things. But once you get to 3 dimensions, it's a lot more work. But the beauty of doing it with vectors is the same idea, same format still works in 3 dimensions. So I'll still be able to dot this. So we've got 15 minus 2, because plus negative 2, minus 4. So 15 minus 2 minus 4 is 9. We have a dot product of 9. And the magnitude of the first vector will have 25 plus 4 plus 4. So that's going to be 33. And then 9 plus 1 plus 4 is 14. So my magnitudes, I said, were 33 and 14. So theta will be equal to the inverse cosine of this. Okay, so again, we didn't really need to do anything differently. Yeah, we had a little more calculating because of the 3rd dimension, but it really stayed the same. So, find the acute angle between these 2 lines. This is kind of a nice bonus of being able to do dot product and being able to use vectors. I think a lot of people, their initial instinct with something like this would be to say, well, I've got to graph these. I have to find the intersection point, and then I need to work from there. Well, here's the thing. Regardless of the intersection point, let's think about these as vectors. Okay? This function has a slope of 2. That means it went over 1 and up 2. So as a vector, it would have the components 1, 2. This, the slope is negative 3. So if you think about it, it went over 1 and down 3. or components, 1, negative 3. Regardless of the intersection point, regardless of what the y-intercept is, that is the way these functions are moving. That's what will affect the angle between them. So, with that in mind, I should be able to, and let me just put this right down here, I should be able to just use my dot product and the inverse cosine. So, 1 times 1 is 1. 2 times negative 3 is negative 5. So that is my dot product. Let me start with that. Over, now let's get the magnitudes. So 1 squared plus 2 squared. So this is the magnitude of this vector is square root of 5. 1 squared plus negative 3 squared. So the magnitude of this vector is square root of 10. So let me write those two down. I have the square root of 5 and the square root of 10. And theta, the angle between it, will be the inverse cosine of this. And of course, you could type that in and calculate. It actually comes out to be 45 degrees. Okay, so this is a nice way to, again, be able to extend and show how much easier it is to do with vectors rather than using law of cosines or law of sines or trigonometry. Finally, how do you know that two vectors are parallel to one another? Well, parallel means a scalar, like a scalar multiplier, will transform one into the other. For example, the vector 2, 1, 3. If I put a scalar out front of, let's say, 3, I would transform the vector into 6, 3, 9. Therefore, these two vectors, 2, 1, 3, and 6, 3, 9, would be considered parallel because the scalar 3 will transform one into the other. Okay? Now, how do you know if two vectors are perpendicular to one another? It's that if the dot product is 0.